I'm Darrell Wallace, Manufacturing Technical Fellow for BlueForge Alliance, and I'm joined here today with Dr. Glenn Daehn, who is the Director of the Ohio State University's Hammer ERC. So Glenn, thank you for joining me today.
Great pleasure. Great seeing you, Darrell.
Good to see you. Hammer ERC, what is Hammer?
Okay, Hammer, start with the acronym, Hybrid Autonomous Manufacturing Moving from Evolution to Revolution. So the idea is most of the time what we do is we start and we think of manufacturing, we think about big productivity processes like rolling, extrusion, machining at large scales. We're going to start with artisan processes and figure out how to make them more efficient, more reproducible, bigger. So one key piece of that is what we call robotic blacksmithing or metamorphic manufacturing. So the idea there is rather than working by adding or removing material, we're going to do what a blacksmith does, and we're going to change the shape of the material. That cuts down the waste. We can also get to near net shape. And we also can improve the properties by forging, and this is particularly important if you're dealing with things like additively manufactured components, things that might have weldments in them already, or things that might be cast. We can take and we can change the structure, get rid of porosity, change the porosity, texture that, and really improve material properties and provide shape. And again, blacksmiths have proven we can do this. So that's really the goal of the center, and we have research programs that deal with design, with materials, with control systems, and also with new tools. New tools are really at the center of what we're doing. So making new robotic blacksmiths, making a lot of tools that really have digital deformation at the core of them. That's really the core of what we're doing.
So if we think about the history of CNC machining, which has been around for a long time, really now, 75 or so years, we've come to accept that type of machining, it's common that it's digitally controlled, motion controlled. But what you're talking about with forging, this really hasn't been done, has it?
Correct. Yeah, it's a new approach. So digital CNC machining and additive manufacturing are both basically based on G-code, where you've got a tool path that either adds or subtracts material. Deformation is different, that when you deform something here, everything else moves. So you need to have a bit of a prediction in mind when you get started, have an idea what you're doing, how you're going to do it. You have to watch that process as you're doing it, and you have to adapt a little bit as you move forward. So, but the basic things you do, cogging, for example, taking something large and then drawing it out into something that might be more cylindrical is something you can do. You can take that then and flatten it or pierce it, bend it, and there's really a huge variety of shapes you can make that way. And of course, if something really has to be precise, number one, you can sense as you go and measure the dimensions and bend or form to get close. And then of course you can always do finished machining after that. So down here at IMTS, where we are right now, we have a booth there. We've got a prototype piece of equipment down there that we invite anybody to go see, and it shows where we're going with all of this. We're trying to mature this very quickly. All the base technologies are there. We just have to push it across the line.
So when I think of forging, I think of a hard-tooled process. And normally if we're shape forging, we'll have tools dedicated to a form. If you're trying to do it digitally, how are you dealing with the need for tooling?
So it's open die forging and closed die forging and your impression die forging. And usually open die forging is used for really big things. It hasn't really been adapted to small things. That's been kind of the realm of blacksmiths and the like, and also tools like English wheels that we're also automating. So what we're doing is we're watching that piece, and if anybody that's played with Play-Doh knows that you can take, or silly putty, you can take and deform and make pretty much any shape you like just with a series of discrete manufacturing operations. So that's one of the key ideas. The other idea we take from CNC machining is even if you have a simple, just a 3-axis mill, by changing the orientation and possibly chucking things at an angle, you can make a huge variety of shapes with something fairly simple. So these are the same ideas that we're really bringing forward. So making the shapes by deformation, so lots of shapes you can make with a little bit of creativity. We haven't really developed the tools to do this yet. And again, once you do that, you can take something that might be 10 pounds of titanium and end up with a part that's about 10 pounds rather than a buy-to-fly ratio of taking 10 pounds of titanium and ending up with a 1-pound part. That's very wasteful. We can conserve the material, start with something that's more or less a cube, and then make pretty much any shape we want out of it. And so it's really a very different approach. Also, it's much more efficient than even powder bed additive manufacturing. There you're usually starting with a fairly narrow powder size. You don't reuse all of the powder. We have a lot of advantages over that. It's still early stage technology, but we think it's got a lot of possible advantages.
So you mentioned additive as a competitor, and certainly One of the selling points of additive is that it's digital, another is that it has a very good buy-to-fly ratio, that in principle very little material is wasted. Talk a little more, if you could, about, you mentioned powder bed, but there's certainly also directed energy deposition. Talk a little bit about why we might want to use digital forming rather than additive. What are the advantages?
And I don't see it as much as a competitor, but another tool in the toolbox that we should have, and that's what we're trying to develop. Again, so if you start with additive, let's first start with how we make our very best materials. Our very best materials are almost always forged or rolled. We use deformation and thermomechanical, and deformation and a thermal history to get there. We typically can't do that with any pure additive process. If you can add deformation to a lot of materials that aren't intrinsically castable. We can break up large phases. We can use all the tricks of solutionizing, deformation, all those heat treating tricks, all of those deformation tricks, and getting truly forged properties out of that. So higher properties are part of that, including the kind of flow lines that we like to see in forgings are a feature that you can't get from an additive or subtractive process. The other is just the overall efficiency of it. We have really efficient ways of making blocks of material at scale, and those are a lot of base exists for that, whereas the base doesn't exist for powders. And also when you go from something that might be bulk to powder, you're taking a bit of that powder, you don't use it all. It's a far more efficient process. It's a much faster way to get large tonnage. The last thing is we can go to large parts very easily. It's very difficult to do things that are much bigger than a basketball. There's examples of that, but certainly open die forging is the way we make the very biggest stuff we need. If you need really large tooling, it's done with open die forging. Lots of parts in submarines and ships are also made by bespoke open die forge parts. We know how to do that. We want to just add levels of control to that to do that at smaller scales and really make that process much more open and eventually democratize it to students. That's part of why we're down in the student section here, is showing students how we can take these basic tools of machine control, CNC design, and do something really new with it.
So that's you talked a little bit about, maybe talked around the types of tools that are needed to implement this, and I know we've had several conversations where we've talked about that many of the tools that you're using to prove this out are kind of off-the-shelf tools adapted. Can you talk a little bit about the state of development? What are you able to do today? What needs to be refined and matured? What do we need to be able to advance this technology?
Yeah, okay. Great question. So the way I think about this, again, I think about the artisan, or kind of our archetypical person is like the tool and die maker. Tool and die maker really does just about 6 things. You're either adding, subtracting, deforming, then you've got other things you might be positioning, inspecting, or running through a transformation of some sort. Welding is sort of a subroutine that puts a lot of those things together. You might grind some edges, bring a couple parts together, deposit liquid metal, let it run through a transformation, which is solidification. We have simple tools for all of that. So rather than think about big processes and how do we understand them, which is part of what we do in engineering research, another topic that we talk a lot about, we're really trying to design from these base operations forward. Think about what's the best way to deform something, what's the best way to run a transformation, what's the best way to inspect. And in a place like IMTS, you see there's amazing tools out there. We're dealing with commercial presses from Promes, we're dealing with commercial induction heaters from Ambrell, and we're putting those tools together in a new way. And the thing that really becomes tricky that once you wade into this is the integration is intellectually kind of straightforward, but with all the proprietary systems, it's difficult to sometimes get everything to talk the way you want and control the way you want. So a lot of people that do this at a high level, these integration systems, they complain a lot about the difficulty of doing that and all the closed systems, and the ROS, robot operating system, is a partial answer. These are the kinds of things that we're leaning into and trying to figure out how we A, do that, and then B, how do we teach students to think for themselves, be creative, and push the technology forward to the next level. That's the other big part, is how do we scale and get lots more students who are comfortable with these things and think partly as a metallurgist, partly as a blacksmith, partly as a software person, because you need all those skills to develop these new technologies.
And am I correct that the scope of hammer goes beyond, we've talked a lot about bulk forming, but the scope of hammer is kind of more broadly traditionally non-digital processes that could potentially, with a new way of thinking, be digitized?
Correct, that's it. So big things that are in it, if we kind of think what is there beyond CNC machining? CNC machining, we think about shapes, think about all that, but I'm a metallurgist basically, and really understanding the metallurgical structure as we go is super important. So I'm still challenged with a lot of the digital pieces of this. The other part that's really important is the control part. If you're controlling something like machining, it's pretty simple. You run a tool path, and there isn't typically a big deviation from what you do. If you're a blacksmith, you're always kind of going, oh, it was a little cooler than I thought. I've actually got to go back and couldn't do as many passes. There's a lot more where you're going to learn, and you might be adapting on the first part, or you might be learning from part number 1 to change the process on part number 10. Once you have that knowledge, we keep getting smarter. You should be able to transfer some of that up into the cloud and actually start using that in other systems. So that's where we want to take this. So there's a lot of work on control. We've got great people in our program who think about control, artificial intelligence, and there's at least 2 levels of control. One is controlling the individual process, like getting the weldment right, and then the other part of that control is how do you control the system, make system level decisions, and figure out what you're going to machine and what you're going to bend and the like. So when you open up that toolbox, make the toolbox big, make it digital, you get lots and lots of opportunities that come forward.
And what's the state of commercial development? I know you're working on some equipment for forging. I think there's some other equipment in this realm in the commercial space.
So we have partners, we're a great partner with Makina Labs out in the LA area. They do something that's basically based on incremental forming, where you've got a pin that basically runs through a piece of material, and there's some awesome YouTube demonstrations that show what they do. They're basically doing something that's a subset of what we see ourselves doing, and they're doing things that are based on sheet topology, and they're also doing that basically at room temperature. They're talking about they have big visions like we do to expand the technology, but that's what they have commercialized right now. We see the opportunity to make robotic forges very quickly, and again, we've got first prototype on the floor here now at IMTS, and that's where we want to take it, is basically start thinking about how we take and transform the material, run recrystallization, change texture, change the phase distribution. To really start improving the material properties on top of the shape. And again, these are all tools. You choose the right tool for the job, and we want to expand that toolbox and again, use that to allow us to make better things like submarines more efficiently, more quickly, and with better properties.
I have always appreciated our conversations and the notion of using the right tool from the toolbox. You know, a lot of people are big fans of additive, a lot of people are dug in with CNC machining, and you've always been very practical about each one has its place and its purpose. So with that, not only do you have the strength of a process or approach, but you also have its weaknesses. So where do you see when digital forming or digital autonomous manufacturing, as you're envisioning it under Hammer, reaches a level of commercial maturity, where do you see it maybe not having advantages? Where is it appropriate and where is it not appropriate?
Okay, what we don't see ourselves doing right now is making parts for large-scale commercial vehicles, Honda Accords or like, they're beverage cans, things like that. We might be in a great place to make some of the advanced tooling for that, getting the residual stresses right in the tool and so forth. That's where we're at. So we don't see ourselves as a high production rate process. It's a high quality process. It's an agile process. And that's what you see most of here at IMTS. Most of the things you see here are for bespoke or high quality, limited lot size parts. That's where we see ourselves at this. The other big question about the right tool is I think the difficulty in this is there are so many tools out there, need so much expertise. I think my advantage is I'm really not an expert at any of these things. I know enough of them to be dangerous, and that's Something that my position as a professor has afforded me is to learn a little bit about that and see where the holes are, and then try to fill in the holes. And I think the biggest hole we have is kind of almost this parochial thinking about you become a welding engineer or an additive manufacturing engineer or a sheet forming engineer, and you see pretty much everything through that lens. And I've been able to bounce around enough that I've been able to, I'd like to think, identify some of these gaps, and then work with a lot of great people who've been able to actually take some of these ideas and start making real equipment around it. And that's harder than it looks, but it's super important. Yeah.
With that broad perspective that you have developed, where do you see the hybrid autonomous fitting into the national landscape in terms of economy, workforce, national security? I mean, obviously our stakeholders are very concerned with production of ships and submarines. Where do you see this all fitting in?
Yeah, local production is really, really important. Again, I'm inspired by what skilled artisan, somebody like a tool and die maker, can do in a limited shop. With just a simple forge, the ability to heat treat, weld, grind, mill. You can make a lot of things within a small volume. And I see that as something that you can deploy both for a positive economy, where you've got tool shops that look like this, where you've got somebody running it. It's tools much like you're seeing here at IMTS, with all these really clever people here using them different ways. But it's a new tool set that cohort can take on and use and build businesses out of. And I think there are multiple places we can see this being used. We see this being used in medical applications. We're doing some of that work now. We see this being used for marine and nuclear, large equipment, all kinds of bespoke equipment, bicycle frames. Who knows where all this goes? So I think there's businesses that can be built around that. The other thing I think is really important is we have a real challenge in maintaining the equipment that we have out there, be it old aircraft or ships or whatnot. And replacing a forging is difficult, and there's lots of stories I've heard where you might have an aircraft bulkhead, and the only option is to take a really big piece of aluminum or titanium and machine down 95% of it to leave this bulkhead. Instead of that, for the price of just a few of these, I think we can take a volume of material, stretch it out, bend it, get the rough shape into it, and then develop that shape. That's the technology that we want to develop. So that can be done at a major aircraft sustainment base. That could also be done at a lower level, right at point of need, where you have the ships parked, or even front lines of the battlefield as a vision. So that's where we want to take all of this.
You're still in the early phases of standing up hammer, I think, right? It's not.
Just had our second birthday, so it goes faster than you think.
Okay.
So we're just starting our third year, and yeah.
So how do folks get involved, and what can they look forward to from Hammer?
Come see us. So website, hammer.osu.edu. We invite people to come in. Base memberships are very inexpensive. If you can sign an NDA, you can get into our deep technical meetings. We want to get that draw in with the community. We have also been working very hard on ways that we can commercialize all of this. So we've got a not-for-profit that we're standing up that has basically all the IP from the 5 great universities coming into it, and we can send that out to be commercialized. And then we are also working on building up a studio and working on investment for that can actually start turning this into prototype products. And we've got things for the medical industry, our agility forge that we're trying to develop with BlueForge, and these are products that we want to get out into practical use soon.
I do have to ask, do you have a dedicated person on staff that develops your acronyms?
We do not, no.
Okay.
Jag Sankar at NCA&T I think he was divinely inspired. It's a great acronym, and all the words actually mean something. It's perfect. Jag pulled that one, like I say, out of the heavens to Jag to us, and it was awesome.
Well, thank you so much, Glenn, for joining me today. Really appreciate you sharing with us what's going on with Hammer and kind of a vision for the future of autonomous hybrid manufacturing.
Great pleasure. Yeah, thanks,
Thank
Darryl.
you.
Yeah, thanks. Cheers. See ya.